Hi guys! Last time we were doing calculations with strong acids and bases, and we were finding pHs and molarities and all kinds of stuff. And those were pretty simple calculations because we know that if you have a strong acid or a strong base, they 100% ionize in water. So if my HCl, for example, was 1 molar, then that means that my H plus is 1 molar and my Cl minus is 1 molar. I know that just from the stoichiometric ratios because all of it, 100% of it, ionizes and turns into H plus and Cl minus. Now that does not happen with weak acids or weak bases. So for example, if I have HF, which is a weak acid, it only partially ionizes. And so some of it stays as molecular HF. And so if I had 1 molar of HF, that doesn't mean that I have 1 molar of H plus, right? I don't know how much of that 1 molar actually ionizes. It could be 20%, it could be 10%, it could be 0.005%, I don't know. So the calculations are not as simple with weak acids and bases. So what do I do then? Well, we use Ka and Kb values. What are Ka and Kb values? Well, Ka is the acid dissociation constant and Kb is the base dissociation constant. And whether it's Ka or Kb, these are basically the equilibrium constants, so KEQ. They just get special names because these are special processes. So since HF is a weak acid, I would write the Ka expression for its dissociation. And just like KEQ, it's products over reactants raised to the power of their coefficients. So it's going to be the H plus concentration times the F minus concentration over the HF concentration. Similarly, I could do the same thing with a weak base. So let's say ammonia. Take that and put it in water. You get NH4 plus and OH minus. So because this is a base, I would write the Kb expression. And it's going to be the ammonium ion concentration times the hydroxide ion concentration over the concentration of the ammonia. So Ka is the dissociation equilibrium for an acid, Kb is for a base. So what do these numbers mean? Well, the higher the Ka value, the stronger the acid. Why? Because the higher the Ka value, that means that I have more ions in solution. The higher the Ka value, the more products I have, or the more ions I have, which means more of it had dissociated or ionized. And so it's a stronger acid. Stronger acid or stronger base means a higher percentage ionization. More of it turns into the ions. So the higher the Ka value, the stronger the acid, or the higher the percentage of ionization. Same thing with Kb. So the higher the Kb value, that means I have more products, and so I have more ions. And so the higher the Kb value, the stronger the base, the higher the percentage of ionization for that base. So Ka and Kb values tell us about the strength of these acids and bases. If you take Ka for any acid, multiply it by Kb of its conjugate base, you will get Kw. Or Kb of any base, multiply it by Ka of its conjugate acid, you'll get Kw. Kw is 1.0 times 10 to the negative 14. So if I were to take Ka for HF, because it's an acid, multiplied by Kb for its conjugate, which is the Kb for F minus, then I'd get Kw. Same thing here. If I take Kb for ammonia, because it's a base, multiplied by Ka for its conjugate acid, the ammonium, then I'd get Kw. Another way that we can tell the strength of the acid is by percent ionization. So the higher the percentage ionization, the stronger your acid or your base. So to find percent of anything, you would take what you're interested in, divide by the total times 100%. So if this ionized, if this was 1 molar, for example, and when we did this in water, we got 0.02 molar of the H plus. Then the 0.02 molar is what ionized, so we put 0.02 molar here, divided by the initial concentration, which is the total possible, right, is 1 molar, and then times 100%. So both Ka and Kb or percent ionization kind of tell you about the strength of the acid in the base and help you figure out, what the pH or what the molarity is. So let's do some examples here. We're going to start with number 1, which talks about lactic acid. Here's the formula for lactic acid. It's an organic acid, and it dissociates to give off H pluses and lactate ion. It's a weak acid, so it partially ionizes. And it tells us that we have a pH of 2.43 when 10th moles of it dissolves in a 1 liter of water. We want to know what is its acid equilibrium constant. So we're solving for Ka. So the first thing you want to do is write out your equation. So I'm just going to rewrite the equation they gave me here. So lactic acid dissociates partially to give H pluses and lactate ion. Now, if you are finding Ka, and it doesn't really matter which acid it is, you can, instead of writing the formulas, you can write the generic formula, which is HA dissociating to H plus and A minus. HA being the acid, so lactic acid in this case, A minus being the anion, which is the lactate ion in this case. So you can make it simpler for yourself if you would like. Next, since I'm solving for Ka, I'm going to write the expression for it. It is the concentration of H plus times the lactate ion concentration over the acid concentration. Okay, so I'm solving for Ka, and I need, since it's the equilibrium constant, I need equilibrium concentrations. So there's no mention of the equilibrium concentration of the H plus or the acetate. It does tell me about the lactic acid. There's 10th molar in 1 liter, but this is the initial concentration. That's not the equilibrium concentration. So initially I had 10th molar, but some of it turned into ions. So I don't know at equilibrium what those concentrations are. So let's make an ice chart. So when you have strong acids or strong bases, you do not need an ice chart because you can use stoichiometry. But when you have weak acids and weak bases, then you definitely need an ice chart. So initially, this is 10th molar, because I have 10th of a mole in a liter, and these are zeros. I don't know anything about the change yet. The only other number I'm given is this. So how can this help me? Well, if I'm given the pH, maybe I can figure out what the H plus concentration is at equilibrium, right? So the H plus concentration is equal to 10 to the negative pH. So it is equal to 10 to the negative 2.43, which is 0.0037 molar. Now this is my H plus concentration at equilibrium. Now, if you know for any of these substances, if you know 2 of the numbers, you should be able to know what the third number is, right? If I started out with 0 and I ended up with 0.0037, then that means the change was that I gained 0.0037 molar. And if you know the change for any of them, you know the change for all of them because the change is based on stoichiometry. So I know that I formed 0.0037 molar. And also for my lactic acid, I know the change is negative 0.0037 molar. I used that much up. So the net at equilibrium, I have 0.0963 molar here, and I have 0.0037 molar here. So now that I have the equilibrium concentrations, I can plug that into my Ka expression. So 0.0037 molar times 0.0037 molar over 0.0963 molar. And you calculate that. I got 1.42 times 10 to the negative 4th. And just like KEQ, we do not need the units for that. Let's try another example. This one's benzoic acid. We have 0.02 moles of benzoic acid added to 1 liter. We want to calculate its pH if we're given the Ka. So this one's kind of the opposite of what we just did. Here we had the pH, we were trying to find Ka. Here we are given Ka, we're trying to find the pH. But you do it the same exact way. So write the equation first. This is my equation right here. This is benzoic acid plus water. This is the benzoate ion and the hydronium ion. or you can write it out if you want. For fun, I'm just gonna say H-benz. It's water, benzoate. I'm going to use it as that, benz minus, and H3O plus. If you even don't want to include your water, you should write H-benz is H plus and benzoate ion. That's fine as well. Whatever. This is just for us to help us. I'm going to write my Ka expression first. It is going to be the concentration of the H3O plus or H plus times the benzoate ion concentration over the H-benz concentration. Okay, and what am I given? I'm given the Ka, 6.3 times 10 to the negative fifth. I don't have any of the other ones, so let's see what other information I'm given. I'm given that this is 0.02 moles in a liter, so initially this is 0.02 molar. I don't care about water, it's a liquid. Doesn't affect equilibrium. This is 0 and 0 to start with. I don't know anything about the change, so I'm just going to say, okay, this is minus x plus x plus x. And so 0.02 minus x, x, and x. So I'm going to plug that into my expression. This is x times x over 0.02 minus x. And that way I can solve for what x is, which is, x is the H3O plus concentration, which is the same thing as H plus, right? And from there I can find the pH. So I got 0.0011 molar. And so pH is going to be negative log of 0.0011 molar, which ends up being 2.96 as my pH. Let's try number 3. It says calculate the pH of 1 molar solution of HF if Ka is 7.2 times 10 to the negative fourth, and then also calculate the percent ionization. So we're going to write our dissociation of the acid first. HF dissociates into H plus and F minus. I'm going to go ahead and write my K expression. H plus concentration times the F minus concentration over the HF concentration. And let's see, I need an ice chart because I need to solve for basically what the concentration of the H plus is at equilibrium in order to get to my pH. So this is 1 molar initially, these are zeros. And we're going to say minus x plus x plus x, 1 minus x, x, and x. So back here, I'm going to write 7.2 times 10 to the negative fourth. That's my Ka is equal to x times x over 1 minus x. When I solve for x, that's going to be the H plus concentration. And I got 0.0265 molar. So my pH is negative log of that. And I get 1.571 as my pH. The other part of the question asked you, what is the percent ionization? So percent ionization is equal to what's ionized over the initial concentration of the acid. Times 100%. And so what was ionized is basically the change, which is your x. So that is 0.0265 molar over my initial, which is 1.00 molar times 100%. And so that gives me 2.65%. So that's crazy. Less than 3% of it actually ionizes. The rest of it, so over 97% of it, remains as molecular HF. By the way, in terms of Sig Figs, remember on the AP exam, Sig Figs are accepted plus or minus 1, so it's not as big of a deal. But just so you know, The number before the decimal in the pH does not count in your Sig Figs. So if your molarity is 3 Sig Figs, then you need 3 decimal places. So this would be 3 Sig Figs, not 4. That does not count in there. Okay, example 4. It says a certain weak acid, HA, is ionized 0.003%, very, very little, in a 1 molar solution. Calculate its acid dissociation constant. So let's try to figure out how we would do that. So it says HA, so let's write the dissociation equation. Let's also write our Ka expression. And let's see what we know and what we're trying to find. So we're trying to find Ka, right? We're going to do an ice chart. Initially, it says it is 1 molar. And so these are zeros. The other number it gives us is this. It tells us that 0.003% of it has ionized. And so that tells us what the change is, right? So what you do is you take this number, the percent, change it to a decimal, and multiply it by your initial concentration. That's going to be your change. It's also going to be the H plus concentration. So this is 1 molar times 0.00003. And so it gives you 0.00003 molar. That is your concentration of H plus at equilibrium. Because that's how much ionized of it turned into ions. So this is 0.00003, which means this is plus 0.00003. This is plus 0.00003. This is minus 0.00003. So at the end, you'd get 0.99997 molar. And this is 0.00003 molar. So back into our Ka expression, 0.00003 times 0.00003, lots of zeros here, over 0.9997. And so this gives me 9.0 times 10 to the negative 10th. And that's my answer. Very small. Okay, let's try one more. It says pyridine, which is a common weak base, has an ionization constant of 1.5 times 10 to the negative 9th. So if this is a base, and this is my ionization, sometimes they call it ionization constant, sometimes they call it dissociation constant, but this is basically your Kb, because this is a weak base. If you dissolve 0.01 moles of pyridine in 1 liter of water, what is its pH? And what is the Ka of its conjugate acid? So we're going to write the dissociation equation first, which is very conveniently written for us here. And we're going to write our Kb expression. If this is an acid, we write Ka. If it's a base, we write Kb. So we're going to write our Kb expression. It's going to be the concentration of the OH minus times the concentration of the cation over the concentration of the pyridine. We don't care about water because it's a liquid, right? So let's do an ice chart. We know that we have a 0.01 moles in 1 liter. So this is my initial molarity. Don't care about water, right? And this is 0 and 0. This is minus x, plus x, and plus x. So 0.01 minus x, x, and x. So let's plug that in. Kb is 1.5 times 10 to the negative 9th. That is equal to x times x over 0.01 minus x. X here is the hydroxide ion concentration at equilibrium, and it turns out to be 3.87 times 10 to the negative 6 molar. So if I want the pH, I need to find the pOH first. pOH would be negative log of that number, which ends up being 5.41. So if I want the pH, it's 14 minus that, which equals 8.59. We also want the Ka for the conjugate acid, which means the Ka for this right here. So Ka times Kb is equal to Kw. So K is what I'm solving for. Kb is 1.5 times 10 to the negative 9th. Kw is 1.0 times 10 to the negative 14. So that gives me Ka to be 6.67 times 10 to the negative 6. And that is my answer.